which are failed and privacy stateful dataflow systems. It's work done in cooperation with Jonas, Spenger, Veresov, and Philipp. So failures are notoriously hard to handle in distributed programming, and even leading IT companies struggle with this. Just to name a few, Google had the outage for around an hour in 2020. Facebook had an outage for around 6 hours in 2021. And Cloudflare had a report outage for around 6 hours in 2020 due to Byzantine failure. And the preferred way to handle the complexity of failure handling is formal methods. Again, to drop a few names, Amazon and Microsoft use them to ensure certain reliability properties of AWS and Microsoft as well as other companies also show interest in them. However, in this talk, I'm not going to talk about distributed systems in general, but about a specific type of them, namely stateful dataflow systems. I will name a few of them. So first of all, Apache Flink, Google Dataflow, as Veresov, and there are also numerous emerging systems of this type. And in these systems, the program is represented as a graph of nodes, which are called tasks, and they're essentially processing functions connected by these edges called streams. And they send messages to each other and process the corresponding events. And the stateful part of the name corresponds to the simple fact that each of these tasks has a state. And once you have a state in a distributed system and failures, that's very hard to handle, because if you fail, you lose the state, and it's very hard to reason about such systems. But kind of the key property of stateful dataflow systems is that there is no need to handle failures manually. And probably this is the reason for the Python use. For example, Apache Flink is used in Uber and Python, and it serves billions of events per second in Python. However, there is a problem with this. This particular property, no need for handling failures manually, have not been formalized generally enough. And namely, this property is known as failure transparency. Particularly, no previous work is applicable to any of the mentioned systems. So, although they claim that they have this property, it is not proven yet. Okay, so the key algorithm used in stateful dataflow systems to handle failures is known as asynchronous bias snapshot. And it works like this. So each stream of messages is separated into what is called echoes, essentially just a set of messages by a special type of message known as barrier, depicted like this. And the algorithm itself consists of 4 steps. So in the first step, each of the tasks just processes all of the messages of simple streams until it nets a barrier on one of these streams, and then this stream is blocked and it processes the others until all of the barriers are aligned. In this case, the task makes a local snapshot and stores it to its persistent local storage and propagates this barrier message to its output stream. And then it switches its mode and starts to process the messages from the next epoch. So that captures more or less intuitively this algorithm, but now to prove something about it, we need to formalize it, and we do so in what we call stateful dataflow model, which is a small-step version of semantics consisting of 3 rules which describe the whole failure part of the system, plus 2 rules to describe introduction of failures and recoveries from them, and 2 rules of delivery. Now I will quickly go through the model, through the rules of it. First of all, the S step is simply a step which allows us to lift a local step defined for one task to the whole graph. So if we have a local step, we can make a local step. This simplifies definition of other steps. The next step is in this case, the task, as was described earlier, propagates the barrier and saves its local snapshot into the persistent storage and starts processing the next step. That's what we call fail-free part system. Now, how do we introduce failures? Well, we just take any of the tasks and mark it as a failure. In this case, a failed task does not do anything. It doesn't introduce noise messages in the system. Yeah. And the recovery rule says that if we have if in our program one of the tasks is failed, then we can erase all of the implied messages and restore the latest common snapshot from the local persistent storages of these tasks. And this, and in this way, we can continue the operation like the failure have not happened at all. So now let's try to capture what failures and further transparency should mean on an example. Let's suppose we have this faulty execution in which we at first processed our program normally, then we met a failure, recovered from it, and continued normal operation. So what should it mean to be failure transparent in this case for a system? It means that in this system there should be a failure-free execution such that the outputs, the observed outputs, each of the steps of this faulty execution can be explained in this failure-free execution. In other words, the outputs should match. For example, we can match outputs like this in this case. And now let's actually define the failure transparency. So, observational explanation is a property which relates to executions, C and C prime, corresponding according to the observability functions O and L prime. It looks like this, but intuitively it just means that no observation unreachable in the explanation execution can be reached in the original execution. So it's essentially a safety property. And also I want to note that the reasonable choice of observational functions is such that they are not decreasing. In this case, we can guarantee that via this definition that there is no situation that explains something from the future, something from the past, like on this picture. Now, observational explainability is a property which relates to systems according to their observability functions and a certain translation relation. It looks like this, not too complex, and essentially it just means that for each execution of a translated low-level program, the original program should have an execution which explains the low-level execution. And again, I want to note that this definition is composable and transitive in a certain sense, and this allows us to build hierarchies of abstractions going from lower level to higher level. So, for example, in our work, we model failure detection implicitly now, but it is possible to prove a separate theory which introduces this failure detection mechanism explicitly, then provide and then combine this theory with the theory which we prove, that is that failures are not correctly, to derive a bigger theorem stating that system with failures and explicit failure handling is equivalent to the failure-free high-level model which we described with theorems earlier. Now the failure transparency is very simple. It's observational explainability of a system that is failure-free part. It looks like this formula, and intuitively means that for each valid program, no execution with failures produces an observation which cannot be achieved in an execution without failures. So I think it captures quite well the intuition which we try to build. And the nice news about this definition is that if you use small-step operational semantics, probably you can also apply this definition to your case and prove that failures can be ignored in your system too. an observable explanation of the original one. So we should maintain mapping of observations while we transform the original execution. And we do this in 3 steps. First of all, we split the original execution into what we call generation by the recovery steps. And then inside each of these generations, we reorder steps, preserving certain validity properties related to causality. We reorder the execution steps and just say that the state to which the recovery is done is exactly the state which we achieve in each of the generations if we discard all of the discarded steps, if we pretend that they never happened at all. And then, because of this equivalence, we can just merge the generations to produce the desired failure-free execution. And now, conclusions. In the result of this work, we have defined failure transparency in a way that it is applicable to pretty much any system explained in small-step operation semantics with explicit failure-related rules. The definition enables easier proofs via this history manipulation proofing related to base validation, at least we do so. And last but not least, asynchronous barrier snapshotting is now proven to provide failure transparency. And we also proven that it is provided, it has liveness,